Alright, welcome for today's section 10.5. Like an overview, I guess, is really what we've got. We got an overview of all this. I think as you go through this section, there's so many different formulas and identities to remember that there's a good chance that you're going to get overwhelmed or you're going to forget something. So this is just kind of supplemental to what we're going to do in class. I'm going to try to give you some ideas here, ways that we use these multiple angle formulas and the product of sum and sum to product formulas, and if you get stuck, or if you forget, or you just need a refresher on things, you can look at this, some of it, all of it, whatever part's most useful to you. So in this we're going to look at 4 different types of angle formulas or trig identities that are in section 10.5, and each of these are a little more complicated than some of them that we had looked at earlier in the chapter. First one is called multiple angle formulas. Alright, those are going to be those where you're given something where the periods have been changed, like in this case sine of 2u, and you can rewrite it so that it's just in terms of u. So we'll look at that here in a little bit. The second one is what we call a power reducing formula. Sometimes you'll have your trig function in terms of a higher power, sine squared or sine to the fourth or something like that, and you want to be able to write it all in the first power, and so there are some formulas that do that. Third type, we refer to those as half angle formulas. So just like what we had the other day, where we had those formulas where we could take an angle and break it apart into 2 angles that we had exact values for. Half angle formulas kind of work the same way. If there's a particular angle that we have an exact value for, and maybe half of that angle we don't have an exact value for that, I'm thinking of maybe a 30-degree angle and then a 15-degree angle, you can use the half angle formula to get an exact answer for that. And then the last type, actually 2 different types rolled into one, we call it product to sum or sum to product formulas. And basically that's just you taking a couple of trig functions and either multiplying them together or adding them together and rewriting them one way or the other if it serves your purpose in a good way. Again, why do you want to do that? Why do you want to rewrite it in a way that looks like this, for example? It's a good question. Maybe the math is easier in that problem. Maybe you have some exact values there that are a little easier to do. All right? So we'll look at those examples here in a bit. All right, so that's kind of an introduction to all of them. Let's look at the one at a time right now. First one we're going to look at is the multiple angle formulas. You can look at your blue sheets, those multiple angle formulas. There's one that turns sine of 2u into some functions that don't have a 2 in front of it. There's a couple for cosine, and there's one for tangent. Alright? Sometimes it's difficult when you're using the cosine ones because you don't know which one to use. So you got to plan ahead a little bit and figure out what your purpose is for that. Important, please remember that putting that 2 out in front does not mean the same thing as putting the 2 in there with the u. If you think back to our work with shifting the functions, the 2 out in front is going to affect the amplitude. The 2 in there with the u is going to affect the period. Definitely not the same thing. Alright, so please don't make that kind of careless mistake. So the example we're going to look at, we're going to solve an algebra equation. So what we've been working on the last couple of days, solving an algebra equation, but we're going to do that when you have that sine of 2x in the problem. This would obviously be difficult to do because you're not going to be able to get the cosine of x and the sine of 2x to factor or anything like that. So what we're going to do is we're going to use that identity that turns the sine of 2x into 2 sine x cosine x. Now it's much easier to factor that. You can pull the 2 cosine x out. And if you notice that I made a mistake, that should not be 1 plus 2 sine x. It really should be 1 plus sine x. I'm going to fix that mistake here in just a second. I'll go back and do that. So I have two solutions here. Remember, I have a product. So I can set each of those two things equal to 0. Cosine of x equals 0, or 1 plus sine x equals 0. Do my work on that. I get a variety of solutions. For the first one, x is pi over 2 or 3 pi over 2. And then for the second one, my only solution for that is going to be x equals 3 pi over 2. Depending on if you want this in an interval, a specific interval, or if you want the general form of it. The general form of it would simply be pi over 2 plus 2 pi n and 3 pi over 2 plus 2 pi n. Again, remember your period for cosine and sine is both 2 pi, so that's why you're going to add that to each of these. Alright, second one we're going to look at. We're going to look at power reducing formulas. Some people, they take a look at these and they don't really understand why they would use them. We're alright with sine squared a lot of times. We know that sine squared is the same thing as 1 minus cosine squared. Same thing with cosine squared. We can manipulate that. But sometimes that isn't helpful. Sometimes that identity doesn't do you much good. And so you have to be able to have some other type of identity that is going to do the trick for you, do the job. Alright, so again, look at your blue sheets, look at those different examples that you have. There is one for sine squared, one for cosine squared, and one for tangent squared. The example I'm going to show you here is just us using this idea as we're going to use it in like an identity. All right, finish solving or verifying an identity right now. But let's try to do it by getting rid of all of the greater powers here. Let's get rid of all of these. So the first thing we're going to do is we'll take sine to the fourth, and we'll just call that sine squared squared. And then we have sine squared, and the idea we just looked at was sine squared is 1 minus cosine of 2x all over 2. If we square that using FOIL, multiply that out as a binomial, you get that. We can apply that idea again now for cosine squared. Take that power reducing formula and plug that in for cosine squared. So you got a very, very nasty looking complex fraction right now. Again, pause, go back, look at this again as often as you need to understand what's going on. So I'm going to take that 4, I'm going to divide it through right now. Divide it through each of those 3 terms on the top. That gives you a fourth minus a half of cosine 2x. That's 1 over 2 divided by 4, which is an eighth, plus an eighth cosine 4x. I can factor that eighth out of all of those terms. I can combine some like terms there. I combine my 1/4 and my 1/8 to get 3/8. Pull that 1/8 out of each of those terms, and I have that. And that is the answer. That's us rewriting this thing without any squared trig functions there. Again, what's the purpose of that? It's a great question. All right, it's just a way to be able to rewrite some of these. Hey, the third thing we're going to look at right now is our half angle formulas. In my own personal opinion, these are not a lot of fun, simply because of the square roots. The square roots make for some very nasty looking exact answers. That's what we're going to use though right now. We're going to use these to find the exact value of sine of 105. Did this problem the other day in class as a sum formula, taking 60 plus 45. Now we're going to look at this by taking half of 210 degrees. So we plug that 210 in. We go and find the exact value of 210. The exact value of the cosine of 210 is negative radical 3 over 2. Work that out, we got 1 plus radical 3 over 2, all over 2. Do the division problem in there, you get the square root of 1/2 plus the square root of radical 3 over 4. This is when things start looking pretty ugly right now. Find a common denominator for that one. Common denominator, that's going to be 4. Multiply the top by 2 there. So you get 2 plus radical 3 over 4. All of that under the square root. You can take the square root of the bottom there, and you have 2 plus radical 3, all under the square root, over 2. That is an ugly answer, but it is technically correct. You want to really rock your brain right now. Try to simplify that. Try to figure out how you can write that in a simpler way. When you figure it out, come back and let me know. By the way, that's going to be a positive answer simply because we know that our original problem, the sine of 105, is positive in the second quadrant. Moving on. Last one. Product of sum formulas. So what we're going to use right now, we're going to use the product of sum formulas, and we're going to use it to write this expression as a sum. So it's a product, we want to write it as a sum. Why? Again, maybe the math is easier in that problem. Maybe it's easier to solve a trig equation if you wrote it in a different way. So again, just using the formulas. Again, look at those blue sheets, make sure you know them, make sure you know where they're at. You can refer back to them, hold on to them, guard them with your life. Alright, don't trade them for food or for expensive jewels. Save them forever. And we rewrite this and combine those 5x and the 4x together into 9x. And we can combine the 5x minus the 4x into x. And there you go. That is a different expression that is equivalent to the original one. Again, why would you want to do that? Perhaps the math is easier in that. If you're using that to solve for something, all right, maybe you need to solve that problem for an answer. Just so you can see how it goes the other direction, we just use the product to sum formula. So let's go the other direction now and use the sum to product formula. Again, know where those are at on your blue sheets. And what we'll do is we'll do an example here where we take two different trig functions right now that would not have very easy exact value answers to them, and we find a way to get an exact answer when we're all done. So for each of these, you would have a somewhat difficult time right now coming up with the answer to these just because they're not on your unit circle. And if you use the sum to product formula, you can take the 195 and 105 and add them together. And when you divide by 2, that's going to give you 2 times the cosine of 150 degrees times, when you subtract 195 from 105, you get 90 divided by 2 is 45 degrees. Now go ahead and plug in your exact values for each of these, and that math is much easier now. And when you're all done, you're going to get negative radical 6 over 2. So not a bad exact answer, pretty clean, pretty easy, given how difficult that problem kind of started. So I hope that these 4 or 5 examples help you, give you an option to go back and look, refresh your memory, try to reinforce what we learned, I hope that makes sense. So good luck when you're working on these problems over the next few days.